we'll start the fourth part of this course, which is find a difference method FDM for advection equations, which is also called hyperbolic equations. We'll work on the simplest such equation, which is ut plus aux is equal to 0, and we're given the initial condition ux 0 is equal to u sub 0 of x. For those who have seen this, this is the solution is trivial. It is simply uxt is equal to u sub 0 of x minus at. Alright, we notice that we can check. Notice that here u sub 0 is a univariate function, a single variate function. Okay, so we can talk about its prime's derivative. So here, if given this, we know that u sub t, right, by chain rule, is u0 prime. Okay, this is at x minus at times, what's that? The derivative of the inside with respect to t, right? dt. The chain rule. This becomes negative a u0 prime. Okay, and we know also ux is just u0 prime times the by chain rule again, but the derivative of x minus at with x is 1. So from these two, we know that ut plus aux is equal to negative au0 prime plus aux, which is u0 prime, which is of course always 0. So simply we know that this is the solution. If you think about it, this is a traveling wave. So at the next, t, this is t, this is x. Okay, a function value here, right? x0, all right, and at t equal to 1. Is a value, this value is carried over to, here is a, here is this x0 plus a, right? This function is sort of traveling along this direction. Okay, so if you have a sine wave, and it will be traveled to the right. Alright, it traveled to the right. You travel to the right. Every time unit is traveled by the distance of a. The same shape keeps traveling to the right. This kind of understanding is very important. It is the idea of so-called characteristic curve. Is an important concept for dealing with hyperbolic equations. So the idea is the following: you have you have a unknown equation, okay, and here's x, here's t, and at x0. Okay, at the x0, you know the function value when t is equal to 0. So there's a function sitting on the x-axis, u sub 0 of x. Okay, and you have in general a curve that is going out of x0 upward. The idea being that if you stare at the equation, all right, for a long time, so you have u sub t plus a u sub x is equal to 0. right? So the trick is that if you look at this A, right, you make that equal to, this is my dx dt along that S, here's S, that curve S, okay, curve S. That's if you do that, okay, then on the curve S, we have, all right, what is this curve? This curve is determined by, at every t, if you parameterize this curve by t, right? At every t, if you give me the corresponding x, you get a curve, okay? This curve is the xt plane. So, I mean, on the other way around, just x t, right? Because we use x-axis. So you give me t, and I have the corresponding x, that will determine this curve. So x is a function of t. If you make that dx dt equal to a, then on this, if you restrict yourself on the curve S, then we have u is a function of x and t, but if you restrict to S, this becomes u of, we know x is like a function of t, right? So this becomes a function of t, and then we can talk about the so-called total derivative, and the total derivative, okay? Total derivative d dt of this guy, of this u of x t. What is this? This is of course, you need to differentiate with x, u sub x, and then you need to define dx dt, chain rule, right? Plus u sub t. Well, we know dx dt is a, so that's a ux plus ut. All right, but the equation tells us that's just 0. This means that if you differentiate something with respect to t, you get the derivative 0. This means that u of x t is a constant along S. That's an important concept. If you restrict yourself along S, then it's actually a constant. But we know one value along this S. But u at x that 0 at t is equal to, we're given the initial condition, right? U sub 0. You're given initial condition. So this means u of x t, right, is equal to u0 at x0 along the curve S. That curve starting from x0, right? X0. So this is a little bit weird. It's not really a solution because it has x0 in it. Okay. This can be resolved because we know we have really used the dx dt, right? This along S is equal to a. This means x is equal to x0 plus at, right? That's the definition of dx dt. Okay, given this derivative is a, and given when t0 it is equal to x0, right? These two things we know this is x equal to x0 plus at along s. Okay, which means what is x0? X0 is just x minus at. Therefore, we basically just proved that uxt is equal to u0 x minus at. That's exactly the same as the solution we wrote down in the beginning. Okay? So we basically solved this simplest equation. If you think about it, so the idea here is that if a is constant, right? If a is a constant, we know we need the characteristic curve is dx dt is equal to a. So we have this is xt plane, right? Xt plane. So dx dt equals to a. The slope of this curve, curve is just a straight line, all right? This slope is equal to not a but 1 over a, because the slope is dt dx, right? Not dx dt. If dx dt is a, dt dx is 1 over a. This slope is 1 over a. And so basically, if a doesn't change with x, then you have all these parallel lines, all these characteristic curves originating from different locations. They are parallel. Okay, they are parallel. This is the case when a is positive. When a is negative, it goes the other way, right? When a is positive, when a is negative, it of course goes this way. This way, okay? It can be quite tricky in the sense that you may have one guy, if a is changing, right? If a is like a is equal to a of x, is x dependent function, okay? So maybe on this location it is positive, but on this location it is negative. So you keep following the characteristic, right? Because we know if we follow the characteristic, the function stays constant, right? The function is constant along the characteristic. Unfortunately, they will intersect. Okay, so this is like x1, that's like x2. So we know if we follow this characteristic, then the function is equal to u0 at x1. If we follow the second guy, we know this function is equal to u0 at x2. So when they intersect, what should it be equal to? Okay, it can be tricky, as you can see, and that's why they say is for this kind of equation, basically conservation law, it can be a full semester of graduate level course. This is the case so-called shock. When there's a shock, the two different values meeting each other, there's a shock. The other case, I'm just plotting the picture for you here. If you have if to the left of this point, the a is negative, so it will go that direction. Okay, to the left is negative, but to the right is positive. Okay, so which means a for this part is positive, a for this part is negative. Okay. Then again, we just plotted this following the characteristic line. Okay. So the question is, what do we do here? There's no in the middle part. Okay. What do we do? There's no characteristic line. that is we have used all the points on the x-axis. There's no characteristic curve that goes through this area. What do we do? It's like a vacuum. Okay, how do we define the solution there? Such some food for thought. If you are interested, you can read more. Just again, the topic would be conservation laws. All right, let's. This is the first course in finite difference. So we're going to go back to the simple case. So we go back to the simple case: ut plus aux is equal to 0, with a being some constant. Okay, constant. And we're going to talk about for five or six schemes. I'm going to write down maybe 4 of them today for you. Some reasonable starting points as you look at this by now. You look at ut. You're right. What do we do is, of course, we like we did for the parabolic equation. We just finished. There's a grid, right? A grid, xj, tn, all right? So you divide this, and then on time, you also divide, okay? So at any location, here is xj, here is tn, so the function value is u at xjtn, right? ujn, that's what we used. So for u sub t, we know, well, if we do forward Euler, for example, that will be ujn plus 1 minus ujn divided by delta t, okay? Plus aux. So when we have ux, there are obviously quite a few choices. It can be d plus, d minus, d0, right? If you historically, because d0 seems to be, you have 2 points, you have high, it's more accurate than the other two. So the first thing that people tried is just you add this is of course add jn, right? Add jn. So it's 1 on the right, uj plus 1 and 1 on the left, uj minus 1 and divided by 2h, right? Approximately ux is equal to 0. Okay, it's equal to 0. And this is so-called explicit scheme. So if you move everything with n on the right, and then we keep everything with n plus 1 on the left, so this is ujn minus a delta t over 2h, right? uj plus 1n minus uj minus 1n. So in principle, n is equal to 0, we have u0, right? u0 of x would give us the uj0, okay? And then you can compute, as we explained a couple of times, you can compute the uj1, right, for any j. And then here n is equal to 0, right, from the equation, from this guy. Now you let n be 1, you can compute uj2, and so on and so forth, okay? So by this way, you sweep the whole xt plane. We're not going to analyze this scheme for now, but presumably you write it down, you can evaluate, you can solve the equation, okay? This is forward Euler in time and central in space, okay? And it turns out, I'm going to just write it down, this is not good. It's not a good scheme. We're going to do some analysis, we'll see next time. But it's not a good scheme. It's, however, the first scheme people tried, because it's naturally d0 is a good approximation to ux. The second is a so-called Lax-Friedrichs scheme, right? LF. What it does is that it turns out, this scheme is not good, but once we replace this guy, this UJM, by something else, so it's very much similar to the first scheme, UJN plus 1, but we're just replacing this UJN by average of UJ plus 1n and UJ minus 1n, minus the same fixed guy, A delta T over 2H, UJ plus 1n minus UJ minus 1n. That's so-called Lex-Friedrichs. This one is okay, right? So this one is okay, but it is dissipative. What dissipative means that if you have some this is like as we said on the last slide, it is a function traveling to the right. Theoretically, if the exact solution is like the initial function traveling to the right, so if your initial function have sharp gradient, for example, ideally it should be this exact guy traveling, right? So it's just different location, but the shape is the same. But by dissipative, it basically means this gets, as time goes by, this becomes a less not as sharp. Okay. Again, we're going to postpone the analysis. The next is a leapfrog, so-called leapfrog scheme. What that is basically you use a midpoint rule. Midpoint rule for the ODE. Right? Remember, the ODE was like integrating from Tn to Tn plus 1. If you do the midpoint, you have this thing. So we're going to get UJM plus 1 is equal to UJM minus 1 minus A delta T over H of this UJN plus 1n minus UJ minus 1n. Alright. So there's a note here. What do I mean by the midpoint rule for ODE, right? This is UT, right? UT. For UT, which is basically we say that we're going to use UJM plus 1 minus UJM minus 1 divided by 2 delta T, because there are 2 steps. You use this to approximate UT at Jn, right? Jxj Tn n. Okay, that's like the midpoint rule. You integrate from Tn minus 1 to Tn, and you approximate this area by the function value. You integrate from Tn minus 1 to Tn plus 1, you approximate this integral by the function value Tn minus 1 to Tn plus 1, right? So this is u of Tn plus 1 is equal to u of Tn minus 1 plus this u sub t dt, right? Use midpoint rule to approximate the integral, which is times the length is 2 delta t. Okay? Right, so this give you the u m plus 1 is equal to u m minus 1 plus 2 delta t, right, times ut, which we know ut is negative aux. So it's negative aux. This guy at Jn, okay, at Jn. So this is just un. I mean, we have all the j's here. Jn minus 1 plus 2 delta t right? You have negative a, of course. Ux, you do the same, 2h, uj plus 1 minus uj minus 1n. Alright, this becomes ujm plus 1 is equal to ujm minus 1, and 2 and 2 cancel. That's why it's minus a delta t over h, uj plus 1m minus uj minus 1m. Right, that's the same as we just wrote down. Okay. The next interesting guy that we're going to again analyze all of them, and we're going to introduce the so-called upwinding, which we're going to do later. But the fourth scheme here is a so-called lax Windroff. So a lot of names. So again, I'm going to try to derive the scheme for you. So the idea here is that your the uj m plus 1, right? This we know is uj m, right? Plus you do Taylor series, Taylor expansion, right? So this is going to be ut, right, times delta t plus 1/2 delta t squared utt, and so on and so forth. It keeps going, but this can be approximated by that. This is just Taylor expansion, okay? Taylor expansion of u x j is tm plus delta t, right, along t. Tm plus delta t is like tm plus 1. So this means the ujm plus 1, okay? This is ujn, okay? Ujn. We know ut because by equation ut is equal to negative aux, okay? So this is going to be minus delta t times aux, okay? And the question is, what is UTT, right? What is UTT? The trick is that, well, we know UT is negative AUX, alright? So UTT is UT and then take another derivative UT, so it's negative AUX. This guy with T again, okay? Well, this is negative AUTX, because UX to UTX we change the order. So this is negative A, that's UT, the whole thing, then X. But we know UT is negative AUX, X. This becomes A squared UXX. So the UTT is actually A squared UXX. Okay. So this is 1 plus 1/2 delta T squared A squared UXX. So this means the scheme is that, well, we know very well how to discretize UXX, right? So this is uj n plus 1 is equal to uj n minus delta t times A times, well, ux is 2h, uj plus 1n minus uj minus 1n, alright? And then we're going to have 1/2 delta t squared A squared uxx, that we used h squared uj plus 1n minus 2 ujn plus uj minus 1n. Okay. we see that this part is basically just the first scheme. The first scheme that we just talked about. Forward oil in time and central in space, right? So basically, the Lax-Winthrop is by adding this term. We fixed the first that scheme that's not so good. We fix the bad scheme, okay? And this kind of technique, which is we're converting the partial derivative with respect to t to the partial derivative with respect to x, right? It can be a higher order, like utt to uxx. This kind of technique, because of the Lax-Winthrop scheme, or this technique is used actually in other contexts, even active area research nowadays. This is so-called Lax-Winthrop type of scheme. Okay. All right. Next time we're going to do some analysis.